Okay, afternoon everyone. Thanks for joining us on this Monday afternoon. So we've got our second webinar of today, and it's Edward Attenborough. So I'll hand you over to Edward. Thank you.
Thanks ever so much, Louise, and welcome everyone. Thanks for joining the seminar today. I'm really delighted to be asked by Paul and the team at Tipton to make a presentation on digital dentistry. Now, usually at this point, I would take a poll of hands to see who got prior experience, but what we're going to do is kind of try and get everybody in the same space and then move forward. We've got quite a lot to cover. It's going to be, depending on how quickly we get through it, about an hour to an hour and a half. My name's Ed Attenborough. We've got a lab based in Nottingham, which is a full service lab doing crown and bridge, implant, ortho, cobalt chrome and acrylic prosthetics and implant work. So we started our digital journey back in April 2000, opening the UK's first digital production centre, and that's grown over the last 20 years to be, I think, the largest in the UK and one of the larger ones, certainly on the radar of the European production centres. So we run 22 one-ton milling machines now, 10 large format 3D printers and 10 two laser sintering machines. So I hope to share with you today some of that journey, some of the mistakes we made, maybe give you a few ideas, hints and tips that we've picked up along the way. And if there are any questions throughout the webinar, there's a chat facility that you can see at the bottom there. Just put your questions in there, and then at the end of the meeting, Louise will probably chair it, and we'll try and field those questions. So without further ado, let's kick off. Here's the agenda for today. We're going to talk about optical scanning and CT scanning. We're going to talk about multimodal scanning, which is a mixture of different modalities of scanning. And then that's going to lead on nicely to image-guided surgery. We're then going to talk about apps that are appearing now for scanning on mobile phones. We're going to talk about computer-aided design, computer-aided manufacture, and then the various workflows in digital dentistry. And just to end, we're going to have a brief off-piste couple of slides into cranial and maxillofacial surgery and the applications of digital technology to those areas as well. So starting with scanning, let's look at desktop scanning. And basically all of the scanners, whether they're intraoral or desktop, today all work on the same principle, which uses an optical scanning technique. And the scanner that you can see here on this slide, top left, was the scanner we started with back in April 2000, which is an optical scanner. And really the technology, although it's moved on, the basic technology is still the same. And the way that it works is, in the case of this particular type of scanner, a laser beam is projected on the die or the model. And as you can see here, bottom left, where the laser light shines on the die, it casts a profile. And that profile is captured by a pair of CCD cameras, a stereoscopic pair of cameras, looking at the profile from two different angles. And using triangulation, the software can then work back from that profile from two different angles, a point in space. And then the die is rotated again, a very small amount, and the next profile is captured, and so on through 360 degrees until the entire profile of the die or the model is captured. And then the software works that set of data back to a point cloud, and from that point cloud to a triangle mesh. Bottom right, we can see a modern scanner, and obviously things have moved on. In the older scanners, they had a platter that rotated under the laser beam. The laser beam was based in this silver part of the scanner here, and that was projected at a fixed angle onto the model. And the stereoscopic cameras were also fixed position inside this apparatus here. And it's basically a 3-axis scanner. So as the platter moves under, each die rotates under the beam or the entire model. Now, In those days, it would take around 5 to 10 minutes to scan a die and up to half an hour to scan a model. So, you know, it was a slow process. Today, we have multiple axis scanners, 5-axis scanners. We can scan multiple dies, up to 32 dies on one platter in a go. And typically, a modern desktop scanner will scan a model in around 10 seconds, possibly less, 10 to 15 seconds. And the scanners today, of course, can also scan impressions. We can skip the model casting process in certain workflows that we'll come on to talk about later. So really the technology still today is the same as it was 20 years ago. It's been miniaturized, it's sped up, but the basic overall principle of scanning is still the same today as it was then, as indeed the accuracy. So these old scanners here were you know, 10 to 15 micron accuracy, and that's comparable with modern desktop scanners. There's a lot of chat about how much resolution, how much accuracy do you actually need in a scanner, and I think a few years ago there was a bit of a debate around that, and salespeople would be saying, oh, my scanner's 5 micron and mine's 2 micron. Well, in truth, you only need the same accuracy as the original recording medium. For silicon or alginate impression, that is in the range of 10 to 15 microns. So there's no point in recording something that's only accurate to 10 to 15 micron to 2 micron accuracy, because effectively you're just creating a very large data set. You're not increasing your overall accuracy, and you know, you're creating a great big data set that's going to take a lot of processing numerically, or transmitting through the internet might take longer. So I would say for desktop scanners, you're looking at 10 to 15 micron accuracy, and that's more than adequate for all indications, including all on 4, all on 6 implant-borne restorations, which are some of the more demanding applications of the technology. So laser light scanning is one optical scanning technology, and we look at this here. I know a lot of you will be thinking about intraoral, but we look at it here because the same principles apply to intraoral. And this is a series of 3 lectures. So in the second lecture, which I think is on Thursday this week, we will talk about intraoral scanning in more detail. And then the final lecture, which I think is on the 22nd of July, we'll talk about 3D printing and manufacturing applications. So this today is an overview of the technologies to give everyone a good grounding and get in the same space. So the second technology that came along a few years later was called structured light scanning. And basically it's the same principle as laser scanning, in that a light is projected on the object, and the pattern that is projected by that light is captured by a stereoscopic set of cameras. The advantage of structured light technology is that obviously we're casting multiple profiles on the object, and therefore per position of the gimbal that's rotating the object, we're able to capture more data in each position. So the rate of data acquisition is much faster. Now these scanners use a DLP light processor, digital light processor, which is a similar technology that's used in sort of PowerPoint projector, and it's projecting a pattern onto the object. Because it's projecting a pattern, it has to go through optics just like a normal projector, and that means that there's only a certain depth of field in which the pattern that's projected is actually in focus. So depending on the position of the model within the gimbal or the height of the dies can affect the accuracy of these devices, because the projected pattern can go out of focus. The other point about this technology is that when it first appeared, it used white light. Now, as we'll all know, with the prism effect of light, white light is made up of many different wavelengths, and as it passes through optics, it diffracts at different angles for each wavelength of light. And with white light, obviously made up of a full spectrum of wavelengths, of optical wavelengths, obviously that causes a certain measurement uncertainty due to what's called chromatic aberration. So what we saw subsequently was that these structured light scanners became monochromatic, and the kind of industry standard has fallen on a blue light. So for recording in the lab, typically we don't need color information. We just need accurate scanning of impressions or models. So we just need very accurate anatomical data, and that will be carried out using monochromatic light. So today, virtually all of the desktop scanners have settled on this technology. And as I say, the scanning speed has greatly increased now, so that we can scan a full model in a matter of 10 or so seconds. And virtually all the scanners that are on the market today are in this format. They are all open. So when they output the data, the scan data, they use a common file format to exchange that data. And that's called STL file format, which stands for stereolithography. So STL file format came from the 3D print sector back in the mid-80s, where they wanted to represent the surface of an object in a digital file format. And the way it works is that it turns the point cloud of individual points that the scanners captured in 3D, X, Y, Z, into a triangle mesh. And it's quite clever because it's almost like a self-optimizing file format for compressing the data, a bit like zip file format, because where there's more detailed anatomy, then you'll have more points and more triangles, and where there's less detailed anatomy, less triangles. So it only has a data density where it needs to record more detailed data in the original object. But as I say, today, STL is the industry standard file format. It does only represent the surface of the object. It doesn't represent what's inside the object. So it's effectively like a triangle mesh shell, but it is the industry standard format, and it's the open format that everybody conforms to these days. So we've looked at desktop scanners. Let's have a quick look at intraoral scanning. So first scanners that came out, CEREC in the mid-80s. Here we see top left. And initially, these devices used a proprietary file format. So there was a move in the industry to try and segment workflows, a bit like the old days of VHS and Betamax video cassettes, if some of you can remember that far back. And of course, once you were in the CEREC workflow, you stayed within that ecosystem. And that carried on that way for a number of years until probably mid-late 2000s, around 2007. And then we saw the march of open systems using STL file format. And today, virtually all of the systems that you see here will either work in the native file format or in the STL open file format. So we can also see here the iTero system. Now that, again, from a line used to work in a proprietary file format. It now has opened up to STL format. You can upload your scans, your intraoral scans, into the cloud. You can select a restorative workflow as well as an orthodontic workflow these days. So again, the file format's interchangeable. The same with the 3M devices, and also here we can see the 3Shape device, which used to have its own file format and now will also work in STL file format. The basic principle in terms of operation of intraoral scanners is basically the same, as I say, as desktop scanning. The physical arrangement of the scanning device obviously has to be different because we have to get the probe or wand intraoral cavity. And the way it works is that basically all the clever stuff is in the handle of the device. And at the end here, there's a mirror at 45 degrees. So really they're all basically designed like a periscope with all of the electronics in the handle and just a simple mirror here at 45 degrees. Usually the mirror is heated to stop it fogging. And this tip here is usually removable so it can be autoclaved. Inside the handle, we again have the DLP light projector or a laser projecting light down the handle of the device onto the 45-degree mirror. The light passes down onto the tooth or prep, is reflected off the tooth, back onto the 45-degree mirror, down the axis of the handle of the device, and is captured by a stereoscopic pair of cameras in the device. So exactly the same principle as the original desktop scanners, but obviously the form factor has had to be redesigned for intraoral use. The tip can only be a certain height because of vertical dimension intraorally, and obviously the window of the scanner can only be a certain size. So the field of view of an intraoral scanner is obviously much less than a desktop scanner. And that means as you progress around the arch scanning, it can only see a small window, possibly a couple of teeth in one image. And as we work around, each of the images might be to the claimed accuracy of the device, let's say 20-25 micron, typically and understandably because of the limitations of the physical limitations of the device, intraoral scanners are not always as accurate as desktop scanners. So each image might be accurate to the claimed accuracy of, I don't know, 20-25 micron. But as the device moves around the arch scanning, the software is stitching all of these individual images together. And each stitching of an image causes its own measurement uncertainty. So once you get from one side of the arch to the other, molar to molar, you might have a cumulative error, which is as high as 60 or 70 microns. So that is something to bear in mind with all intraoral scanners. A lot of the scanners these days do record in color, and I think that is really important, certainly from the lab perspective, because these devices are all optical devices. They can only record what they can see. A path of light is in a straight line, and if the prep is subgingival, then clearly we're going to need retraction cords to enable the device to record that. And if the device records in color, that's very helpful for the technician, because we can see the difference in texture and color between the soft tissue and the tooth to help us identify the margin. Now, a lot of these devices now also using a texture file format called PLY, so that on top of the triangle mesh, which represents the anatomy of the prep, they're layering a texture, so they're recording texture as well. And that's almost like a skin that's put on the wireframe mesh, the triangle mesh of the anatomy. And again, texture information is really useful in helping us to identify where the margin is and where things are. So the way that these work is that quite a lot of them now work in a sort of dual mode. So they'll record the actual prep using monochromatic light, the anatomy of the prep, so that they minimize the measurement error due to chromatic aberration. And they will then switch briefly to white light to capture color information to layer over the top of the accurate wire mesh that they've recorded. So the technology has really come on very fast. And again, as I say, we will talk on Thursday's presentation about this in more detail, but you know, they were quite large devices. They're much easier to handle now. They're all fully open. and you can export data in STL up to the cloud for multiple different workflows. So I think a really interesting conversation to have, because with COVID and cross-infection control and SOPs and heaven knows what else, you know, taking classic impressions is an extra risk. So we are seeing a big move at the moment to an acceleration of the adoption of digital technologies over the last few weeks. And I think, you know, it in terms of moving impressions around and disinfection of impressions versus intraoral scanning, it's certainly an argument to be made there in terms of your overall strategy in the new normal, as they say, of COVID management. The other thing is, of course, that they do give a very good impression for the practice, if you'll pardon the pun, to the patient, and they're great communication tools as well. So I think, you know, in summary, very quickly, and I say you can get more on Thursday, but, you know, the time is now for, they've come of age, intraoral scanners, and the technology is certainly there. The hardware is certainly there. So, you know, I wouldn't be worrying now that you're going to buy a hardware that's going to be obsolete within a few years, because the technology is pretty much there. The software is still moving very quickly, but of course, software can be upgraded and updated quite easily. It's the hardware that one wants to make sure is a little better longevity. So I show this one to give some idea of size and how quickly things move. In terms of the intraoral scanner, you can see the size. This is only a few years ago, and if you compare that to size of some of the ones now that are a little more than a handpiece, you can see that the hardware really has matured very quickly. Talking about the software very quickly, and I'm going to come on to CAD later on, I think it's useful that chairside software allows the clinician to identify the margin. Certainly that can help the lab if there's an opportunity to review the scan and identify the margin chairside before it's uploaded into the cloud. As I say, we'll come on to talk about CAD chairside versus lab a little later on. And the arguments and merits for both. But certainly in terms of immediate feedback of your scan, I think it's really important that you have an opportunity to review it, to identify the margin. The software now can also identify caries and can also let you know whether you've done an appropriate prep for the indication of the individual restoration. For example, have you allowed enough vertical dimension for the restoration? Has the appropriate margin been cut, and so on and so forth. So very useful immediate feedback as well, which is another argument. So the second scanning modality that I want to talk about is CT scanning. And this is slightly different in its file format to optical scanning. CT scanners, even a few years ago, were very expensive, perhaps out of the reach of general dental practice, but they have come down a lot in price now, sub 50K, and the dose of radiation that's given, for example, for a quadrant is typically less than a flight from London to New York. So in terms of justification for taking a CT scan, the risk assessment for the dose of radiation that patient's been given, the threshold is perhaps lower than it was previously, which I think is increasing the rate of adoption. Also, the fact that obviously the devices themselves are coming down in price. Now, obviously it works with ionizing radiation. It effectively outputs in a file format called DICOM, and this file format is different to STL in that it's a set of slices through the scanned object, almost like a sliced loaf, and each slice is a JPEG image. So rather than hard and fast triangle meshes with CT data, you're talking about grayscales measured in Hounsfield units. And part of the process of data management is in converting that data from the raw data into 3D data, called a process called segmentation. So in terms of CT scanning, typically the space between each slice or JPEG image is around half a mil, and obviously you can go lower than that to 0.25 mil, but the higher the resolution of the scan, the higher the dose of radiation the patient's going to receive. So there's always that balance to be made there. Scanners these days will scan certain volumes only, so you can control the volume and radiation exposure that the patient's getting very accurately. These devices will scan to high resolution, so you can actually put an impression, for example, in some of these devices and switch to high resolution mode, and they can scan to 15 or 20 micron. Obviously you wouldn't subject a patient to that level of dose, but just to say that they can provide another functionality there. So interesting technology and very useful for surgical planning, as we'll come on to talk about. All of the scanning, whether it's CT or optical, also is subject to a measurement error in data processing. So in optical scanning, you go from a point cloud to a triangle mesh. In CT, you go from a set of slices, JPEG images on grayscale or Hounsfield unit to a triangle mesh through a process called segmentation. But again, we need to remember that there's a measurement error that's introduced by virtue of the data processing, by virtue of the software. And with intraoral scanning, it's more about filling in areas of data that have been missed by the software automatically, correcting double scans, correcting bad stitching of individual images together. But we need to have that at the back of our mind, that all of it's not exactly what you see is what you get. And there's another step in this process that's almost invisible to us, which is the data manipulation process that does introduce a small amount of error. So having looked at optical scanning and CT scanning, let's look at multimodal scanning. What's this all about? Well, this is, as its name suggests, one or more modes of scanning on the same treatment plan. So the way it works, or it used to work in the old days, is that we would make a scan stent for a patient. You can see here, this is a simple pressure formed stent. The teeth in this are acrylic mixed with 10% barium sulfate, so that they will have a different radiographic density on the final CT scan. And on the early scans, what we used to do was put gutta-percha balls, as you can see here, these little purple-pink balls here in the sulcus of the stent, to help us to have anatomical landmarks that we could co-locate the images together. So the patient would then go have a scan stent and go and have a CT scan, and they would scan the patient wearing the stent, and then they would scan the stent on the model, and then using the software we could combine the two images together. Now, because we're able to scan the stent optically on the model, we're able to scan it to a much higher resolution, to sort of 10 or 15 micron, as opposed to the 20 to 25 micron of CT scan. So we can then merge the two data sets together using the landmarks to create a composite image, which has the required accuracy. And that's basically the foundation on which image-guided surgery is built, which we'll come on to talk about now. So basically, you scan the model using an optical scanner, or you could use an intraoral scanner, but preferably an optical scanner. And you import the DICOM data from a CT scan. And then you use those two scans to merge them together to create a composite image. And you can see here, there's an alignment process. So you can see here, the purple is the optical scan and the brown is the CT scan. And you can very quickly see it. I include this slide because this was partway through the image matching process, but you can see the resolution of the CT scan in terms of the slices here. And you can see it's much lower than the optical scan. The other advantage of this technique is that we quite often get noise or artifact on CT scans caused by standing restorations, fillings, metal crowns, PFM crowns, so on and so forth, and that can cause noise on the CT image. But by merging the data with the optical scan, we can eliminate some of that noise when we create a composite image. Now, the great thing about using CT, of course, is that you can measure the bone density and see where there is adequate bone for placing the implant from a clinical perspective. And you can see here on this slide where we're planning to place two lower anterior implants. Now, all of the softwares come these days in open file format, so they'll accept STL from intraoral scanners, from desktop scanners, either of models or impressions, and DICOM data from any CT device or CBCT device. They also have an open library of all of the different implant systems. So all of the different fixture heads and types and sizes of implant are all in an open format that can be loaded into this software, so that we can plan the surgery with the most appropriate length and diameter and type of implant for the particular indication. We can also trace out soft tissue, so for example nerves, and make sure that when we plan the surgery we're well clear of those. Once the treatment plan's complete, and with this software it is quite nice, this is Co-Diagnostics, but there are other ones out there. Obviously from a technician's perspective, we like this software because it also lets us see in real time the planning surgically of the placement of the implants, which might be carried out physically remote from us in the practice. And we can provide an input for the restorative part of the treatment to make sure that the position or planned position of the implants is appropriate for the planned restorative protocol. I.e., can we correct the angulation with this particular system? Is it possible to correct that angulation with abutments or not? Where's the screw access hole going to emerge? So on and so forth. So really nice communication tool between surgeon and technician, and also a great planning tool because we can have all of the team involved in the input of the overall treatment plan to deliver the best outcome for the patient. Once we've settled upon where the implants are going to go, we're able to design a placement guide in the software. And these may be tooth or mucosa borne, this one obviously tooth borne. And the software creates for us a cylinder within the guide, which we can then press fit metal sleeves. And the software knows what size those metal sleeves are. Obviously, there are libraries of those components for guided surgery, so that when you press the sleeve in, it's an interference fit. And then the sleeve itself guides the shank of the drill, so it can very accurately control the position of the drill in orientation, angulation, and depth. And typically, these systems are provided with a set of what's called spoons, which are concentric sleeves that you can put in. So you can put a concentric sleeve in, do your pilot drill, take that concentric sleeve out, and then do the main drill. So very accurate placement. We quite often fenestrate the guides so that you can make sure they're fully down on the teeth, as you can see in this particular example. And here you can see a composite image of the whole process. So remember that this is also connected to the restorative workstation in the lab. And because we plan the treatment together and we know to a known degree of accuracy how the implants are going to be placed, we can start to digitally plan in CAD the restorative element, making custom abutments and a provisional restoration, so that the whole treatment plan can be carried out and the patient leave with a provisional restoration, typically in an hour. And this is very useful, and it's great communication tool again. So here we can see a simple 4-unit anterior lower bridge that we did in this combined protocol, which Dental Wings and Straumann call Synergy. But there are a number of different open packages out there now that will carry out a similar process. So we've talked about 2 different scanning modalities, CBCT and optical. And we've obviously shown how this can lead to combined treatment planning as represented in this final slide of this section. There's one extra scanning modality that I want to come on to talk about, and this is quite new. And this is the use of mobile phones or handheld devices for scanning and the apps that go along with it. So there are a number of these, and obviously people can contact me at the end. I'll provide my details, but certainly Bellus 3D is one of the apps, and these Bellus 3D only runs on Apple, on iPhone, and I think it's the later or more contemporary versions of Apple, the ones with the cameras on the back in a triangle shape. I think it's iPhone 11, but these apps will scan in 3D. So you can basically do a 3D color scan of a patient's face using a mobile phone. And again, using the principle of recognition of anatomical landmarks, we can then take, for example, a CT scan, as we can see here, and we can move the Hounsfield filter on the CT scan to segment out soft tissue, as you can see we've done here. And then we can pick anatomical landmarks on that soft tissue and overlay the scan from the mobile phone. So we're now seeing this being done quite a bit in practice, where a clinician will call a patient in, they might do an intraoral scan, and they might do a Bellus 3D scan, and then they'll ask the patient to pop out to the waiting room, and they'll upload the data in real time to the lab, who will then do a virtual diagnostic wax up, and then download that data back chairside for the patient to be called back in from waiting, and we can then communicate to the patient the treatment plan, show the patient how they'll look if they decide to have the treatment done, and a great communication and sales tool. And I think we're going to see the emergence of mobile phone based apps for scanning across the board. There are other apps for Android as well, and as I say, I can provide those details at the end. But we're going to see this as the 3rd modality of scanning. So we'll have sort of optical scanning, either intraoral or desktop, CBCT scanning, and then we'll have optical facial scanning using apps, all coming into the same data and workflow. So, having talked about data acquisition and data file formats, we're about 45 minutes in now, so we're about halfway through. I'm going to come on to talk about computer-aided design. We've got the data now, it's in a common file format. How do we process that data? How do we do our designs? And do we do those designs chairside, or do we do them in the lab? So I suppose the first thing to say is that software has come on a long way in the 20 years that we've been in digital dentistry. And basically now anything that you can do with a wax knife in the lab, you can do digitally in the software, either chairside or in the lab. And the chairside software is really powerful now. And I think one of the things to say here is that a lot of technicians, and I speak as a technician, saw chairside CAD/CAM, CEREC and similar as a threat, but we don't see it that way, because actually, as far as we're concerned, the digital footprint is expanding out chairside, and that's good, because the more of the workflow is digital, then there's more that we might have a part to play in that digital workflow. Now, certain things lend themselves to being carried out chairside, and certain things don't. As long as the data capture devices, even if they're chairside scan and mill units, are there, then, as I say, there's more opportunity to get involved in the workflow. So we actually see the fact that people invest in chairside systems as a lab, we see it as a positive thing, because we know they'll be suitable for certain indications and not for others, and we can certainly help at some point in that digital journey. So CAD, the automated proposition for the design of a crown chairside is very good. One of the things that we do see with a lot of the software is an issue with bite, and this is partially around the recording of the bite, in that typically with an intraoral scanner you do a double scan, you do a full arch scan of the lower, of the upper, and then you do a buccal bite scan. But obviously the stitching of a buccal bite scan hasn't rolled over the occlusal surface of the tooth, so you're losing some of the three-dimensional data to allow the stitching to occur. So the merging of the three scans together using anatomical landmarks on the buccal bite scan will always have a certain amount of measurement uncertainty or error, and that may in part lead to issues with bite on restorations chairside. Obviously, one can design the software so that it has a pre-programmed gap. So it's reducing the bite by a certain amount, it's keeping the restoration out of the bite. Whether that's ideal or not can be debated. But certainly the initial CAD proposition for chairside crown and bridge is very good. And of course we can mill lots of materials very easily chairside, composites, hybrids, that's composites that are filled with perhaps nano ceramic material. There are lots of materials that lend themselves to milling chairside, but there are some materials that perhaps are better processed in the lab, and it comes to a question of how do you value your chairside time? I think that's probably the way to look at it. We can mill zirconia chairside, but then would one want to then have to wait for it to go through a 3 or 4 hour sintering cycle and stain and glaze it, color the unit, and possibly do a certain porcelain build up on it? Or would that be better done in the lab? Similarly with Emacs, for example, again, it's got to be milled, it's got to go through a crystallization phase, and then it's got to be surface stained and glazed. All of these processes take time, and that is time that you could be seeing patients. So is it certain processes seem to lend themselves more to being processed in the lab, whereas other materials and processes, perhaps provisionals, temporaries, will lend themselves to be done chairside. And from our perspective, that's fine. Things should happen where they're most appropriate to happen. So again, whizzing through chairside CAD, as I say, anything that we could and still do in wax can now be done digitally. Crowns, bridges, inlays, onlays, veneers. The software is very comprehensive now, and I would say, again, talking about technology, just as the intraoral scanner and desktop scanner hardware is there now, I would say that the CAD chairside or in the lab for crown and bridge is there now. It's very advanced and comprehensive, and not found wanting in any respect or indication. Again, we can do complex implant work digitally, and this would typically be done in the lab. To pick up the position of the implants, particularly if the fixture head, of course, is subgingival, the way that it works is that we screw in a special type of abutment into the implant, which we call a scan body. And two things about that. Firstly, the top of the scan body has a known shape so that the software can pick up the position very accurately of that scan body. And because the software knows from its library the geometry of the entire scan body, it's able to extrapolate back from the supragingival scan body shape to the subgingival implant fixture head very accurately. So it's able to work out where the fixture head is. And again, these particular workflows we find sometimes can be challenging on full arch work with intraoral scanning. And we would counsel people to take impressions perhaps as well as intraoral scans for this kind of work, just to have a safety check, peace of mind that there have not been any stitching errors with the intraoral scanner. So for intraoral scanners, perhaps, obviously orthodontic work, shorter span bridge work, individual crowns in nose on, nose and veneers and so on, perfectly suitable, and also for removable prosthetic work that we'll come on to talk about. So that's a very quick overview of computer-aided design, and there's a lot more to that as well. That could possibly be a lecture in its own right at some point, but let's come on to talk about digital manufacture now, computer-aided manufacture, CAM. And basically there are two different, excuse me, there are two families of manufacturing. There's so-called subtractive manufacturing, which is milling, that I'm sure a lot of you are familiar with, and the so-called additive manufacturing, which is 3D printing by another name. So first of all, we're going to talk about the software used for computer-aided manufacture. And when we output the design from the CAD process, that's in an STL file format. So it's still in the same triangle mesh file format as was imported into the CAD process. But when we manufacture, we need to translate that triangle mesh into a set of commands for, be it the milling machine or the 3D printer, to actually manufacture this. So again, thinking about the measurement uncertainty that was introduced by turning the point cloud into a triangle mesh, or the individual JPEG slices of a CBCT scan, a DICOM data into a 3D image by segmentation, we also now have to translate our CAD designs into something to manufacture. And again, that's going to cause a certain uncertainty or error. The way this process works, which is common to both subtractive and additive, is that first of all, we want to make batch process our manufacturing. So we use what's called a nesting program to put as many restorations on one block of material or in one manufacturing cycle or 3D print cycle as possible. And this is a bit like a game of 3D Tetris. It's merging the various individual crowns and bridges together to fit as many onto the build platform as possible. And of course, for milling, those objects can't just be suspended in thin air, so they actually have to be attached to the mother material, the billet of material that they're going to be milled from, by connectors, and we have to plan where those connectors are to make sure that they're not going to adversely affect the margin of the crown, for example, if they're positioned on the margin. And obviously all of that's got to be fitted together. And once we've nested all of the restorations together and we've got all of their connectors or screws or supports in the case of 3D printing, we then have to turn that batch into a set of commands that the milling machine is going to execute to cut out the object in the block. And to do that, Obviously, milling, it's a bit like a contours of a map. You have to cut the object away. That's why it's a so-called subtractive process. So you'll start with a certain size milling tool and move down in the milling tool to a smaller and smaller until you get the final mill. But basically, we're taking a triangle mesh and turning it into a set of contours to mill. So that's basically what the CAM process does, be it for milling, subtractive, or additive in 3D printing. It's common to both, and it's a similar process with both. So first of all, we're going to talk about subtractive milling processes, and obviously this may be chairside or in the lab, and it's interesting to talk briefly about those and the relative merits of each. Now, basically, it's you pay your money and you take choice, and basically, the more the capability of the milling machine, the more you can do with that milling machine. So a desktop or chairside milling machine will have a certain capability. It might be able to mill single units, maybe smaller billets with up to 3 unit bridges in of certain types of material, but it may not be able to mill others. So we often find that the little chairside milling machines don't mill metals, and they perhaps don't mill some of the harder materials, particularly if they're not a wet milling machine. They won't mill the lithium disilicates or emaxes of this world, but most are wet mills now, and can mill single units, veneers, inlays, onlays very, very well. Again, would you want to be spending time firing those in a furnace, sintering them or crystallizing them and staining them and glazing them, or would you select the materials, composite or hybrid materials that can be used for immediate restoration of provisionals or temporaries? The basic machines are 3-axis, so they mill in X, Y, Z, and then they have a 4th axis, which is a tilt here. And then for more advanced machines, you'll find that they have 5-axis. So they have X, Y, Z, where the spindle is here that's controlling the milling tool, which is cutting the objects out. And then they also have tilt and yaw on. So they have an A and a B axis. They have X, Y, Z, which the actual milling tool runs in, and then an A and B axis, or tilt and yaw, which the actual gimbal that holds the material is in. But they all work on a similar process. Obviously, the more robust, the larger the machine, and the heavier the machine, but the more accurately than it can mill. So, for example, for large implant-borne restorations, you just wouldn't be doing that on a chairside mill. That's something that's going to be done in the lab. But really, digital workflows segment themselves quite naturally, and things happen where they need to happen. And it would be difficult to justify in most practices investing in a 150, 200,000 pound milling machine or a 350,000 pound laser sintering machine. That's the sort of thing that needs to be batch processed through a lab or production center nationally. So there's economies of scale here, which lead to sort of certain machines and technologies being used in the lab, and certain technologies being used in the practice, and that's entirely natural and proper, as we'd expect. As you can see, when the bridge is milled out, it has to be attached to the billet by sprues, and these have to be cut back afterwards. So the CAM software that we were talking about earlier is planning how this bridge is going to be nested within the overall billet of material. It's going to plan where these sprues are going to go. It's going to plan the orientation of the bridge within the blank, which is quite useful, particularly if you want to improve milling from the perspective of the path of insertion. So we can kind of rotate the bridges within the blank to get a better or more accurate final mill, because remember that we're converting from a triangle mesh to a set of contours. But once it's milled out, obviously we remove the bridge, we cut the sprues with a disc, and then we hand grind back and finish and start processing. Now, just as the workflow was segmented in the early days from a software point of view, with proprietary file formats, and that was overcome by the open movement and STL file formats. So there was a segmentation in terms of the actual materials and the fixtures for the materials. So they all came with a proprietary bayonet format, and that meant that they could only be loaded into certain machines. And obviously, again, about the same time, mid-2000s, we started to see the emergence of adapters that would load proprietary blanks. This is Emacs here, for example, in the pre-crystallized or purple state. This is TelioCAD, which is a composite PMMA like material. But they both have proprietary formats that wouldn't load into a generic milling machine. So most generic milling machines work these days for the desktop machines with a 98.5 millimeter diameter blank disc, up to say 26 millimeters deep. But obviously these proprietary formats didn't lend themselves to that. So then people started manufacturing adapters so that you could load these blanks into the generic milling machines, and obviously overcome those closed workflows with an open solution. So that's milling very quickly, and there's lots to talk about there with milling that we could go on to talk about, but I'm very mindful of time. This next part is to talk about 3D printing, and here I give a brief overview of a few of the technologies, because there are quite a lot of different technologies in 3D printing, but I'm going to talk about 2 or 3 of them that have specifically been adopted and are used in dentistry. And the first one is SLA, or stereolithography. And the way that this technology works is that you have a liquid, which is a photopolymer, and basically it has a photoinitiator in it, and when it's exposed to light, it polymerizes and solidifies, that we're very familiar with our restorative materials. The clever thing about this process, and the slide I'm showing here is a technology from around 2005, which is one of the first ones we started working with from EnvisionTech. The patent is now out on that, and there are lots of different systems based on this technology that we'll come on to see shortly. Basically, within this system, you've got and we're looking sideways on here, you've got a vat, and in that vat, you've got that yellow photopolymerizing liquid, and the basement of the vat is a glass plate, and underneath the vat you've got a projector, again like your PowerPoint projector, a DLP light processor projector. And the way it works is that they divide, it's almost like the DICOM CBCT process in reverse. They take the 3D triangle mesh object and they divide it into a set of slices, and then they project a mask, which is a negative of each of the slices, onto the bed of this vat of photopolymerizing liquid. So the projector's down here projecting upwards onto this liquid, and where the light shines, the liquid polymerizes and goes solid. And then this basement, which is now fully pulled out of the liquid, is actually immersed in the liquid where the liquid is polymerized on. It moves up a level, and then the next slice is projected, and so on until level by level you gradually pull the solid object out of the liquid, a bit like Terminator, I suppose, if you've seen those movies. So great technology, very clever indeed. Couple of limitations to be aware of, and they apply as much today as they did to the technology that we see here. The first one is that there's only one material here, and so these things can't grow in thin air. They have to be attached to the base. So if you look very carefully here, you see a little corner on there. That's the first layer that's printed down, and then these cones actually have to be attached to that layer by sprues. And so it's quite important where they're positioned, because the machine itself doesn't 100% cure the material. It only cures it to the point where it's solid, but it's not 100% cured. So after you take this out and you remove the build from the plate with a kind of fish slice, you then have to wash it in isopropanol to remove any excess photopolymer, and then you have to put it in a light box to cure. Now, we all know when materials cure, they have a tendency to shrink. So they change dimensionally. So the objects that come out of all of these little desktop printers aren't the finished product. They have to be post-processed or cured, washed and then cured. And in doing so, they change shape dimensionally. The second problem with this technology is that it's only printing in one material. So as I said, these things can't just hang in thin air. They actually have to attach to the build platform by supports. And where those supports attach to the object and are removed, they obviously cause little pot marks, a bit like sprues, which have to be ground back. The third problem with this technology is that because the material isn't fully cured in the machine, it can have a tendency to sag between the supports. So it's quite important where the supports are positioned, and there are in the CAM softwares algorithms for automatically positioning the supports so that the user doesn't have to spend a long time doing that. They did in the old days, they used to have to do that manually, and it used to take hours to do. But still, we need to have in the back of our minds that these things aren't producing fully cured output, and there might be some distortion in there. And the final issue with these machines is that, again, they're based on an optical projection. So they suffer from distortion due to the lens. In the center of the build platform and the center of the lens, that's the least distortion. As you get further and further out on the build platform, the edges of the build platform, the distortion gets greater and greater. So a couple of issues to bear in mind. That was technology back in 2005. It's moved on a long way, but a lot of these issues are still there with the modern desktop printers, the little Formlabs that we'll come on to see shortly. So again, how the object is positioned in the build platform, whether it's positioned vertically or horizontally or an angle, that will affect the accuracy of the print, and it will distort to a different extent depending on its orientation. Typically, the sort of accepted wisdom with these desktop printers now is to print at kind of 45 degrees to minimize the distortion for horseshoe arch models, for example. So here you can see a couple of bridges that have come out of this process. And as you can see, there's the platform that they built on. They're attached by sprues to that platform. They need to be washed in isopropanol to remove any excess uncured monomer, and then they need to go into a light box to be fully cured. The second technology that we looked at was wax jet printing. Now, this was altogether more familiar to us. And basically the way it works is you've got two print heads here. You can see a blue one and a purple one, and they're running two different waxes through each print head. And the print heads are very much like the heads in the inkjet printers, but they just jet a single jet out here of wax rather than ink. And the way it works is that you have the print heads moving across the build platform in X and Y, backwards and forwards. And then once a full layer is done, the whole build platform, in this case, rather than moving up like the DLP, it moves down a level, and then the next level is put out, and so on until you get the final build, which is built up of millions of droplets of wax. Now, the interesting thing is that this is printing in two materials. So one of the limitations that we saw in the DLP process, the SLA process, initially have been overcome, because now the build or object that we're making is encased in a support wax. So it's supported all the way around and it can't sag in between. And the interesting thing, the clever thing about this is that the two waxes, the purple and the blue wax, have different melting points. So if you put this in mineral oil at 60 degrees C, you can dissolve the supporting wax away and you're left with the final object. And still today, you know, 15 years later, these machines, these solid-scape machines, produce really beautiful wax ups. And at the start, when we were looking back in 2005, we were principally looking at 3D printing then for automating wax ups. Now, the problem with this technology is that obviously the material has got to solidify. So it takes time for each droplet to lay down and change from the liquid to the solid state, and that makes them very slow. So we found that these wax jet machines weren't really cost effective in a lab environment, but they are still very popular in jewelry, and they do provide an exquisite wax up that lends itself to a more jewelry-like application. And then the third technology that we looked at was kind of a combination of the two, and this is what we settled on. This is 2007, I think. And this is technology from 3D Systems, PolyJet technology. And basically, it's patent 3D Systems, but it's a combination of the two previous technologies that we've seen. So we overcome the support issue by printing in a support wax, just like we did with the wax jet technology, and we're printing the final object in a different wax. But what we're doing here is, rather than having wax for the build object, we're using a photopolymer, and rather than jetting out a single droplet at a time, we have a print head with thousands of droplets coming out, a matrix of droplets all coming out simultaneously. And as the droplets come out, a UV light exposes them and cures them instantly as when they hit the build object. So we've overcome the speed issue, we've overcome the support issue, and this technology was the one that we finally settled on. Although these days we also use Objet, which is a similar PolyJet technology. Looking at additive manufacturing or 3D printing in dental, and starting to look at some of the workflows now. Obviously, we've talked about 3D printing wax ups for crowns, and it doesn't really make sense to mill precious alloys. If you know, the billet itself would be a fortune, and the swore for any one time in the machine, the scrap would also be a fortune. So economically, it doesn't make sense to mill precious metals. So the so-called CAD cast process, where you digitally produce the wax up and then invest and cast it, is still very popular for that application. Another application is wax ups for cobalt chrome dentures for partials. Again, it's quite difficult to mill those, although they are being milled in PEEK now, and we'll come on to talk about that perhaps a bit later on. But certainly produce really nice wax ups. Wax ups for injection molding of flexible denture materials, again, ideal process. Models for pressure forming of retainers and aligners, ideal, absolutely ideal. And printing models directly and surgical guides. So printing 3D models for building restorations up on, and printing surgical guides that directly can be used in a CE marked material for intraoral use are another application of these technologies. As we see the technologies move on, so in 3D printing, we're seeing the materials science move very quickly, and we're seeing more and more materials which now can be used for direct restoration rather than indirect casting or injection molding or pressure forming process. So more and more of the 3D printing materials can be used directly intraorally, but you have to be very careful about the workflows. You have to be very careful about what you're doing, mixing and matching materials with different technologies, and we'll talk about that a little more in the third of this series on 3D printing in dentistry. So to come bang up to date today, SLA or serial lithography printing, Formlabs is one of a number of different desktop technologies. These machines around £3,500, open format machines, great for printing models to work to. They do have some of the same issues as we looked at with the DLP processing in terms of distortion, in terms of position and support. Again, the material isn't fully cured at the end of this process. It has to be taken out and post-cured, so we still got those issues. We still got to decide where we position the supports to avoid distortion and how we orientate the object within the build platform to minimize the distortion. The spherical aberration issue that's caused by the optics are eliminated within the Formlabs process, because rather than using a DLP projector, it uses a laser, and the laser position is controlled by a pair of mirrors that move the laser around the build platform. So we don't see any optical errors in this process. It's linear, whether you print on the middle of the build platform or the edge of the build platform, you're going to get the same accuracy. But the other issues we talked about are still there. Would I use this kind of desktop technology for all-on-4 or all-on-6 implant models? No, I probably wouldn't. Would I use it for crown and bridge, simple crown and bridge models, individual crowns, on-lays, veneers? Yes, I would. Would I use it for models to vacuum form bleaching trays or pressure form bleaching trays or aligners or retainers? Absolutely, yes, I would. And we are seeing materials come here now for direct restorations as well, CE mark materials, but again, we have to be careful about the process. Principally, we need to be aware of the fact that the material is not fully cured in the machine. So the photo initiators within the photopolymers are not particularly nice materials, and certainly not ones that we'd want in the oral cavity. So we need to be 100% sure, if we're printing a direct restoration using this technology, that all of the photo initiator is used up and the monomer is fully cured. So really important considerations there. The other technology that we looked at was polyjet technology. Again, that's akin to the 3D systems and latterly the object stratasys machines. The great advantage here is that they are completely linear over the whole build platform, and they really lend themselves to batch processing, but the machines are more expensive. They start around 25,000 and go up to 60,000 or more. So perhaps more difficult to justify in a practice setting, but for production or batch production in a lab, 100% linear. Again, they use a support material which can be dissolved away, and they produce very accurate models. So polyjet for our more demanding applications in crown and bridge and implant is our preferred technology. The third additive manufacturing or 3D printing technology that is applied in dentistry is laser sintering, and this is a slightly different process in that it layers down the raw material. The print material is in a powdered form rather than in a liquid form. So it's a powder of the final material, and it layers down the layer of the powder, and then it melts the powders together with a laser, again controlled by two mirrors. So the laser moves across the build platform, sintering the material together, and then another layer is put down and it sinters it again. Now, again, these technologies are only printing in one material, so they have to attach the final build to the platform with sprues, which have to be removed off. Obviously, that has its own limitations, but we can directly print metals with this technology and extremely cost effectively. So we can see here a set of PFM copings that have been printed in one of these laser sintering machines, and you can see the supports that are attaching to the base. So each of those supports has got to be removed and ground back. That's quite hard work. You take the whole lot off with a bandsaw and then you remove the supports individually manually. But if you nest a lot of copings or units within one build, it does become a lot more cost effective. So these machines here are typically anywhere between 150 and 350,000 pounds. Clearly, that's not going to be something that's placed in every practice. It lends itself to a national production centre such as ours. But it does mean that you can produce batches of these quite cost effectively. More cost effectively, certainly for cobalt chrome, than milling, because milling, as any of you will know from dental school, milling, cutting cobalt chrome is hard work, grinding away at it. It's hard stuff. Tungsten carbide burrs are expensive. And it's not particularly kind on the milling machines either. So to mill copings digitally is expensive, although it is a scalable process, whereas to laser sinter them is a much more cost-effective process, but obviously much higher capital investment. And we can also use this process for manufacturing cobalt chrome partials. Now, again, like any manufacturing process, each different application, be it partials or copings, needs different parameters, but we've been able to perfect nesting both partials and copings together on the same build platform, and that can subsidize or cross-subsidize the price of one against the other and bring down the cost of the laser sintered partials. And these are exquisite units, really accurate. You do have to relax the alloy by a thermal process in a furnace before you cut off the base, the supports, because the process does inherently build a stress in the alloy. But as long as that's done correctly and the process followed, then they're extremely accurate for all on 4, all on 6, or more complicated work. And here we can see a combination of both processes, and you really know when you're on top of your game here. So at bottom left, you can see a laser sintered partial framework, and that is sat on a polyjet printed model. And so you've got there two totally separate manufacturing processes. And I can tell you, when you press that framework onto the model, it's just that beautiful click, no rock at all, and it fits absolutely perfectly. And you know when you can do that with two completely different manufacturing processes and achieve that level of accuracy, that you're really on top of your game. On the right, we can see a milled PEEK framework, and there's a lot of work going on here at the moment, and PEEK is becoming a popular material in a number of different indications. There are additive manufacturing processes for PEEK now as well, using different technology to that we've discussed, FDM, or fused deposition modeling, extruding a filament of PEEK onto a model, or laser sintering. And those processes are just going through CE marking now, so we'll see 3D printing of PEEK in the not too distant future. Very quickly, and looking at the time, we've got about 10 minutes to run. Let's have a look at some of the workflows, software workflows in initially crown and bridge. So this is what's called a hybrid workflow, in that we've printed the bridge framework digitally, and then we're going to do CAD cast to manufacture it. So basically, for the wax jet process, it's absolutely identical, because the wax burns out in exactly the same way as it would do by hand. For the photopolymers, we had to adjust the process a little to match the expansion coefficient of the build, the 3D printed wax up, with the investment, to make sure that it didn't crack the investment as it burnt out or leave any residual carbon. But once these things have been figured out, and they are possible, then the process works very nicely. So just to show you here, and there is a photopolymer or SLA DLP print as well, investing, casting, devesting, despruing, and you can see really there that the casting is as good as you would see with any hand wax up. So you can achieve a really nice result with these hybrid or digital workflows. And then very quickly, just running through building up by hand, on this classic workflow, a PFM, and getting a nice final result. Obviously for ortho, that's well established now. You'll have all heard of Invisalign and others, aligners, planning orthodontic setups digitally. Now the software is very well advanced to do that, to see what's possible, occlusion analysis, PARS analysis, treatment outcome simulation in software now is all quite mature. And this is for removables or for fixed orthodontic work. And we're seeing technology where the arch wires can be formed robotically, and the placement stents for the brackets 3D printed, so an entire digital process. And then for removable prosthetic devices, we're seeing haptics come in. So these are like 3D mice. They're basically provide a force feedback, almost like a virtual wax knife. So you take this pen out of the inkwell there, and as you move it around, as you touch the object, you can actually feel the object. There's a force feedback in each of the axes of this device, and you can actually feel the wax flowing off the pen virtually. And in doing so, we can digitally survey a model. This is for a cobalt chrome prosthesis. We can see the undercuts. We can digitally block it out. We can carve into the undercuts to engage the clasps. We can lay down the grid and the plate, the connectors. And once we've done so, we can then 3D print the wax ups. Now here you can see we put a bar across there from the heels. This is to stabilize the wax up, because with the 3D printing process, we don't use a refractory model. And obviously when the investment sets, it's an exothermic process. So it's just to make sure that these wax ups don't distort as the investment sets, and cast them accordingly. So a really nice second example there of a hybrid workflow where we're mixing digital wax up with classic investment casting. And we can do some really lovely designs, things that actually would be very difficult to do by hand, grid that's much smaller, items that would be very difficult to wax by hand, we can do digitally. These are some more recent examples where we're experimenting with supports and making the supports very thin, possibly 100 micron, so that we can twist them off by hand. It reduces the amount of work that's required to finish the object. So the technologies here in laser sintering are really coming on quite rapidly and delivering some absolutely stunning results. And then finally, in the last 5 minutes, a quick little off-piste tour of cranial maxillofacial. I mentioned this really out of interest to open people's ideas to where this technology might go in the future. And I think we can be really proud of ourselves in dentistry, because dentistry is really integrated and adopted digital into virtually all of its workflows, as I hope you've seen now from this presentation. And in fact, this is now held up as the industry example of the adoption and integration of digital technology. So some of the 3D companies, 3D printer companies, for example, are entirely basing their market plans and business plans around dental now. So we've really led the way in dentistry, and as we've done so, now follow other applications such as cranial maxillofacial and orthopedic. So polyjet printing is being used for printing CT or DICOM or MRI rather models for surgical planning. We can use the same technology using CT or MRI data to restore patients' anatomy. In this case, it was a case we did for a patient who was a professional squash player, and unfortunately the opponent's racket had caught his zygoma, and he had an orbital floor fracture that had been repaired with 2 generic Medpor implants, which had both failed. And we went on to try and digitally manufacture an orbital floor for him using CT scan data. So we took his right side, mirrored it across to the left, designed a plate, and then reconstructed it, and that was a full success. Some of the other applications: cranial plates, custom-made orthopedic implants, and so on and so forth. So a huge range of ideas there that this technology can be applied to, and perhaps we'll talk about those in a later session. But for today, that's it for me. I'm done. Thank you ever so much for listening. And Louise, if you want to come back in, I'll be happy to take some questions.
Hi Ed, yeah, I think there's just one question in the Q&A. If you can you see it at the bottom, or?
Let's have a look. Just getting that up. So yes, the scan app is Bellus 3D. Let me just type that in for you. BELUS 3D. That's for the iPhone. Yeah. Hopefully you can see that, everybody. Is it possible to get a replay of the webinar? Yes, I'm sure. Louise, do we have?
Yeah,
is that on YouTube?
The replays will go out next week. They'll be on Vimeo, so they'll be sent out to everyone who's registered. So yes, they'll go out next week.
Okay. Yeah, absolutely great. Any other questions at this stage? No. Okay. Well, that's great. Thank you very much indeed.
Yeah, brilliant. Thanks ever so much, Ed, and we'll see you again. I think it's Thursday, isn't it?
It's Thursday for the intraoral scanning lecture. Yeah, it's quite a popular one, that one.
Yeah, brilliant. So we'll see you on Thursday. Thanks ever so much.
Thanks ever so much. All the best.
Bye-bye.
Bye.